All right, hi everybody. Today we're going to take a look at our day 2 lesson, which is on graphing systems of inequality. So yesterday we spent some time with writing systems of inequality. So now we're going to take a look at what that looks like on the graph and what the solutions appear to look like on the graph as well. We're going to use the Desmos graphing calculator as our technology today to do our graphing for us. So first I want to just review, when we graphed linear inequalities last week, like this, y is less than 1/2 x plus 2, we saw that we had a boundary line, and then one side of the boundary line was shaded, and the other side was not shaded. So in terms of, got a question down here, where are the solutions? The solutions for this inequality are in the shaded area, all along the shaded area, and keeping in mind this line extends in that same angle, and then the shading is going to always be below that line. If it's on a dashed boundary line here, those are not solutions, as we talked about last week. Okay, so in terms of where are the solutions, they're in the shaded area of this single inequality. What we're going to look at today is we're actually going to look at a system of inequalities, meaning we have two or more inequalities put together on the same system. So when we graph an inequality, we know that we're going to get a boundary line and then half of the graph shaded, one side of the boundary line. When we put two inequalities together, what we do is we graph both inequalities and they overlap. So we have this red boundary line that's dashed, and it appears to be shaded below the red line. We also happen to have this blue boundary line here, and everything is shaded below that as well, which it looks more like to the right, but technically it's below the line. So what we're looking for, where are the solutions to both of the inequalities? Well, this area over here in red, let me place a dot over there, make it a little bigger. All right, so this point right there, that is actually only a solution to the reddish inequality, whichever one that was. The dot up here is only a solution to the blue inequality because it's only shaded in the blue, but it's not shaded on the red side. So what we're looking for solutions to something like this is anything that's shaded where the two shadings overlap. So if I were to kind of draw this line, try that again. Kind of shade in all the way up to those boundary lines, but not crossing those two boundary lines and when they where they intersect. Okay, that would be our solution zone, or where our solutions are going to occur. All right, so it's not going to be in the unshaded area. It's not going to be in the area that's only shaded in blue, and it's not going to be in the area that's only shaded in red. The solutions are going to be where the blue and the red overlap. So that's where it's a little bit different with systems of equations, inequalities today. So I would like to go through an example with you real quick on our video today. And we are going to graph this system of inequalities and determine if these ordered pairs are solutions. And we're going to use Desmos to do that. Open up our Desmos calculator. Make this just a little bit smaller so we can see everything. Actually, you know what? We don't need to see it. We have everything in here already. I'm just hiding the view. So the first inequality, y is greater than or equal to negative 2/3 x plus 1, looks like this. We have our solid boundary line, so points on the solid boundary line are solutions to that inequality, as well as anything that's in the red shaded area. The other inequality, we have a dashed blue line, so points on the dashed line are not solutions, but anything in the blue shaded area is a solution to that inequality. What we want to look for is where do these two overlap when we show both of them. So we see that we have an area that's shaded only in red, so that's not going to have solutions to the entire system. We have an area that's shaded only in blue, that's not going to be any solutions to the system. We have an area that's not shaded at all, so that's definitely not a solution. What we have for the solutions are this area off to the right that is shaded in red and in blue. It's where those two areas overlap. That's where the solutions to the systems exist. Now we have two different boundary lines along this, this area that's shaded. We have a dashed boundary line. So if anything happens to fall on that dashed boundary line, of the dark shaded area, it's not a solution. The other boundary line over here is actually solid. So if it happens to be on this boundary line, as long as it's along the darker shaded area, it's a solution. If it's on this solid line over here, it's still not a solution because these two areas aren't solutions. Okay, it's got to be on a solid boundary line of an area with solutions in it, where the shading is overlapped. Okay, so let's take a look at these ordered pairs and determine which of these are solutions. So let's start with 4, 3. We've got a green dot. There it is. Let's actually label that. And we can see that 4, 3 actually appears where the red and the blue overlaps. Maybe it's easier to show one at a time. It certainly is a solution to the red inequality, and it is also a solution to the blue inequality. Okay, so it is a solution to that system then. The next ordered pair is 1, 3, plotted in purple. So if we look one at a time, we can see that that ordered pair is a solution to the red inequality. And it is not a solution to the blue inequality because it's on the boundary line and the boundary line is dashed. So 1, 3 is not a solution. Let's look at the next one, -2, 4. And in this case, it's our black dot. We can see that it's a solution to the red inequality, but it is not a solution to the blue inequality. So that is not a solution to the whole system. 6, -3 is down here. Oops, forgot to label again. 6, -3 is right on the solid boundary line, and it happens to be on the boundary of the area that has all of our solutions. So because it's on the solid boundary line, right along the area that has the solutions, that actually also is a solution. So notice the difference between the purple dot, which was not a solution because it's on a dashed line, and the red dot that is a solution because it's on the solid boundary line. -1, -5 is a solution to the blue inequality because it's in the blue shaded area. But notice it's not in the red shaded area. So it's not a solution to all of the inequalities in that system. So that is not a solution. And last we have -6, 1, which is over here in the area that's not shaded by either one. It's not shaded in red or blue. So that's really the one where it wasn't a solution to either inequality. So we can see here it's not a solution to the red inequality, and definitely not a solution to the blue inequality either because it's on the opposite side of the shaded area. So the only ordered pairs that were solutions here was 4, 3 because that was in the area shaded in red and blue, and then 6, -3 because that was shaded, it was on the solid boundary line. It was a solution to both inequalities. So 4, 3, 6, -3 are the only two that are solutions. All right, then I do want to touch base on the 4 examples that you looked at in the day 1 homework. So problem number 1 was Brantley's Bakery, where he was making batches of cookies and number of cakes based on the amount of flour and time that he had. And if we were to actually graph this system of equations that we wrote, system of inequalities that we wrote earlier this week, let's take a look at what that would look like so that we could see so that we could see what the solutions look like. So let's go through this one at a time. So here's just our standard graph. If I graph the first inequality, I can see, kind of move this over a little bit, I can see that we have a solid boundary line, and we have all of our solutions are in the red shaded area. Now keep in mind, this goes on forever, right? Look at these numbers, -600, -400, and that's going to keep going. So yeah, even these negative numbers are solutions to this inequality, even though it doesn't necessarily make sense for this problem for Brantley's Bakery. It's still a solution to that inequality. When I look at the second inequality with the, this was the amount of time that he had to bake, I see that I have a solid boundary line again. And again, it's shaded off to the lower left-hand side. If I zoom way out, I can kind of see what's going on there. If I overlap those, So I want to look at where do those two shaded areas or the solution sets overlap? What do they have in common? Well, it's this area that's shaded in red and in blue. So not up here. This is only shaded in blue. This is only shaded in red, but the solutions are all these different ordered pairs and points shaded in red and in blue. Keeping in mind, if I zoom out, I mean, that extends all the way out. It just keeps going and going and going the more I zoom out, right? Okay, so that's a really big area of solutions. However, we have two other inequalities, these two other constraints on how many batches of cookies and how many cakes he could make. So the green one here was the one where it represents that he can't make any negative numbers of cookie batches. Okay, so if I were to zoom out, it's just going to be that the X value has to be positive. It just can't be over here on the negative X side. So X could be 1 batch of cookies, 2 batches of cookies, 10 batches of cookies, 20 batches of cookies, and so on. We also know that Y has to be non-negative, so it could be 0 cakes, 1 cake, 2 cakes, 3 cakes, 4 cakes, 5 cakes, any ordered pair up above where the Y value is 0. If I look at the solution set for just these two inequalities, I see that they're going to overlap in this upper right-hand quadrant, basically the first quadrant, where my X and Y values are non-negative numbers. Okay, so it's not over here in the purple area, it's not down here in the green area. My only solutions can be up here in the first quadrant of the graph. So when I kind of put those concepts together and I look at where do all of my shaded areas overlap, and they can get really confusing when you have 4 of them. That's why I like to turn these off and look one at a time. Okay, so when I look at the red and the blue, it's kind of below the red line, but also down below and to the left of the blue line. But we said it's to the right of the y-axis, because x has to be bigger than or equal to 0. It also has to be above the x-axis. So where did all of those overlap? It's this shape right inside here. I'll zoom in a little bit on that shape. It's a little hard without the, I don't know if I can get all of those to appear, but we have these corners, which we'll talk about later this week, our vertices. And that kind of gives us our area, our shape, where it's actually possible for combinations of cookie batches and cakes. So we see that 2, 2, I don't know if I can get my coordinates to come up. I can't. But 2, 2 would be a solution. Okay, he would have enough flour to make 2 batches of cookies and 2 cakes, and he has enough time to make 2 batches of cookies and 2 cakes. 4, 2 is possible. So he could make 4 batches of cookies and 2 cakes. Up here would be 2 batches of cookies and 6 cakes. That would be possible. But as soon as I go across that line over here, the 4 batches of cookies and 6 cakes, he can't do that anymore. He either doesn't have enough flour or he doesn't have enough time. Okay, so the only possible solutions are going to be inside this area where it's shaded the darkest. Okay, so to kind of go back to our lesson here, I did want to just share with you, this we came up with together, but if you wanted to double check as a bonus for those of you that are actually watching the video today, here you can double check your answers to the day 1 homework. Here's your system of inequalities, and here are your variables for the Dutch Bulb Flour Company. And then number 4, Max was trying to get a couple jobs working at Buck Hill and shoveling snow on the side. So here is your system of inequalities and your variables for Max's problem. All right, see you guys later this week.